integration in this video are about the area and the volume between the curve and the Cartesian axis. We can use integration to find the area and the volume because one of the application of the integration is about to find the area from the given curve and also the volume from the given curve when it is rotated about x or y axis. We start from the definition first. To find the area between the curve and the x-axis from this graph, we can divide the graph into several rectangles. You can see that I have several rectangles with the width of delta x and the height of the function. This is the function. So the height will be depends on the function itself. For example, if the function is about x squared, for example. So when I draw it, it will be like this. So when x equals to 1, it will be equals to 1. So if I make a rectangle, so the height will be equals to 1. But if x equals to 2, it will be equals to 4. The height will be 4. So the height here, it will be depends on the equation. So I can make several of rectangulars to calculate the area between the curve and the x-axis. But sometimes we will find difficulties here because this calculation will be not accurate since we have the extra and lack of the area of the rectangle here. So the calculation, it will be only an approximation. To find the area between the graph and the x-axis, we just sum the rectangle. So the area of the rectangle is the width times the height. So it's the fx, the height, times the width. And then we sum. This is sum notation. So we sum it. So the area 1 plus area 2 plus area 3 and so on until area n. Now, how do we prevent the inaccurate in calculation because of the extra or lack of the area that we cannot find? So we can increase the number of rectangles by decreasing the width. So if we increase the number of the rectangles into an infinite number, so we can do that if the delta x here will be very small, approximately 0. The delta x, the width should be very small. So we can change the delta x into dx notation, and using the limit function, the sum of the area of the rectangle for the small difference can be written in the form of integration, integral of fx times dx. So therefore, we can use the integration of a function to find the area between the curve and the x-axis. So in this case, we can have two types of estimation. So if we use, this is the function, and we have only several rectangles, so this will be an underestimate. Because the area of the rectangle that we find here will be below than the actual area, since we have the blank spot here. This is underestimate. Or sometimes we have the rectangle that greater than the graph itself. So the area here will be overestimate because the area that we found here will be greater than the actual area. That's why using the integration will prevent the under and overestimate from the calculation, because now, since the number of the rectangles become very many, I can draw it small, very small rectangles, so the area will be very accurate. It will be accurate. So using the integration, we can assure that the area of the graph and between the graph and the axis will be accurate. So we will see the area between the curve and the x-axis is given by the integral of fx dx from a until b. So a and b are the border in the x-axis. But also we can find the area between the curve and the y-axis by the integration of fy dy from c until d. So c and d in here, this is dy, so c and d will be the border in y-axis. A and b will be the border in x-axis because this is dx. So you have to see in which axis that you want to find the area. If you want to find the x-axis, so you have to integral fx in terms of x, yeah, with variable dx. But if you want to find the area between the curve and the y-axis, so you have to find the f in terms of y with the variable dy. So in here, for example, find the area A and B from the given equation. So x minus 1, and x minus 2. So we will find the area of A and B. We find the area of A first. The A is the area between the curve and the x-axis. So that means we will find integral of y dx. Yeah, so we can simplify. The area of this is integral from a to b. Fx is y dx. So we integrate from 0 until 1. This is from 0 until 1 because the area A is between 0 and 1 of the function x times x minus 1 times x minus 2. If we expand the function, we will have it as x cubed minus 3x squared plus 2x. And then we integrate this to have the 1 over 4 x4 minus 3 minus x cubed plus x squared, and then we put the border 0, 1. So it will be 1 over 4 times 1 to the power of 4 minus 1 to the power of 3 plus 1 squared minus, we put 0 in all. So the result will be equals to 1 over 4. So the area of A is 1 over 4. How about the area of B? The area of B is the same. So integral of y dx, but the border are from 1 until 2. So integral the same function x cubed minus 3x squared plus 2x with the border limit from 1 until 2. So we have the same thing, 1/4 times x4 minus x cubed plus x squared from 1 until 2. And then we do the definite integral calculation. So it's 1/4, 2 to the power of 4 minus 2 cubed plus 2 squared minus with 1/4 times 1, 4 minus 1 to the power of 3 plus 1 squared. And then if we calculate this, we will have equals to negative 1/4. It is negative because it's below the x-axis. So this is negative 1/4. If it is below the x-axis, it will be negative. Since area cannot be negative, so we have to remove the negative sign from area B. So we put the absolute sign there to remove the negative. So it will become 1/4 plus 1/4 equals to 1/2. So the area of A and B together will be equals to 1/2. The question arises maybe, why don't we just calculate the area from 0 until 2 directly without dividing it into two regions, A and B? Let's check the integration for the limit from 0 until 2. The result of the integration will be 1/4 x4 minus x cubed plus x squared for the border 0 until 2. So we calculate 1/4 to the power 2 to the power of 4 minus 4 minus 2 to the power of 3 plus 2 to the power of 2 minus with 0 minus 0 minus plus 0. So the calculation here will be 1/4 times 16 minus 8 plus 4 minus 0. So this is 4. So 4 minus 8 plus 4 is equals to 0. So from here, we can see that if we calculate the area from 0 until 2 together at the same as if we just direct to find the area between 0 until 2, the calculation, the result of the integration will be equals to 0. Why? Because this function contains two regions that have equal area, 1/4 and negative 1/4. So they are canceling out each other. So that's why in this case, we cannot find the area using the border 0 until 2 because it contains the area on the top of the x-axis and bottom of the x-axis. So they will be cancelled out. So we have to make sure that the area that we are looking for are always in the positive x-axis if we want to just do the single calculation. But if in this case, we need to separate it. So we cannot use this. Yeah, we cannot use this since the graph contains the positive region and negative region. Find the first quadrant area bounded by the curve between 4 and this is 4 and 0. And when x equals to 0, so we have to find the c. So we put 0 plus 2, so y equals to 2. Now we are looking for the area of curve and the y-axis. So the integration now should be in the form of integral fy dy. Fy dy is x. So that's why we have to change the y equals to x squared plus 2 into the x equals to square root of y minus 2. Plus minus because one is positive and another one is negative. Since we will have the first quadrant, so we will take the positive. So it's integral between 2 until 4 of x dy. In this case, we can just directly put 2 and 4 because the area is only in one side, not two sides as before. Before, the area are on the top and bottom. So we have to split it into two regions. But in this case, because they're only one side, so we can just calculate it directly. So we integrate this one using the normal power rule. So this is y minus 2 to the power of half. So we integrate this and we will have y minus 2 to the power of plus 1, yeah, 3 over 2, and then 2 over 3. So we put the border 2 and 4. So it's 2 over 3 times 4 minus 2, 3 over 2, minus 2 over 3, 4 minus 2 minus 2, 3 over 2. So it will be equals to 4 square root 2 over 3. So this is the area. This is the exercise. You can try this by yourself. Next, move on to the area between the curves. If we have 2 or more curves, how do we find the area? So we see the definition. If we have a function f and g, so we can see here that if I have integral of fx, I will get the area between the curve and the x-axis. Integral of fx dx is the area between the curve and x-axis. So I will get this area. But if I have integral of the function g, integral function g x dx, that means I am looking for the area between the curve gx and the x-axis. So I will have only this one between the g and x-axis. So how do I find this one? So I have to remove g area from f area. So that's why I just minus it. So find area of fx and then minus area of the gx. So find the area of the top one minus with the area of the bottom one. Or we can just combine the integration if the boundaries are the same. So the general formula to find the area between the curves, between two curves, so we just subtract fx minus gx, while fx is the higher function here, in the higher position, and the gx should be the function at the bottom. So here are some suggestions in solving the area of using the integration. First, we have to sketch the area to know if there is an area under the x-axis. And then after that, we can determine the boundaries A and B. So it depends on our sketch. If we can just do it directly, for example, like this, A and B, so we can just use the integration of A to B. But if we have integration like this, there are two regions, one on the top of the x-axis, the other is lower than x-axis. So we have to divide into two regions, so A, B, C. So integral AB of fx plus BC integral fx dx. So we have to split it. That's the third method. We construct the equation, the definite integral. And then after that, we just integrate it easily and calculate it using the definite integral method. For example, calculate the area of the segment cut from the curve and the line. So we can sketch it. This is the curve, quadratic, concave down. So here is the curve. And the line y equals to x, this is y equals to x. And the area between the curve and the line should be the shaded region here. So for the first method, we sketch it. The second method, we determine the boundaries. So we can find that the boundaries between the two curves and the line using the simultaneous equation. So 3x minus x squared equals to x. So x squared minus 2x equals to 0. So x minus 2 equals to 0. So x equals to 0 or x equals to 2. So here is 0 and here is 2. So A is 0, B is 2. And then we set up the definite integral. So the top one will be x times 3 minus x. So integral of x 3 minus x dx minus integral of x dx. And we can combine, so integral between 0 until 2. So this is 3x minus x squared minus x dx. So simplify, integral 0 to 2x minus x squared dx. So x squared minus 1 over 3x cubed. And then put the boundaries 0 until 2. Put it in the calculation, 2 squared minus 1 over 3 to cube minus 0 minus 0 and equals to 4 over 3. This is exercise, so you can try it. Next, we move to the volume. So using the definition of the volume, so if you have an fx and we have the height of the fx, y equals to fx, yeah, the height, and we rotate it about the x-axis. So we will have the line rotated to become a circle with radius of fx. So the radius will be equals to fx because the fx is the height of the line. This is the height. This is the height. So this is equals to the radius. The height is the function itself. So when we rotate it, so we will have a circle with radius r equals to fx. Now, if we want to find the volume, so that means we can find a volume of a small cylinder with the thickness of delta x. So we sum the volume of the small cylinders So it's become sigma area of the circle. This is area of the circle. So it's pi r squared times height. The height is the delta x. For the small value of delta x, we will change it into dx. So using the limit again, limit for n approach to infinite, the sigma pi r squared delta x will change into integral pi r squared dx. And r is the fx, so integral pi fx dx square, because the radius is square. So I can just move the pi out the integral sign. So fx square dx from A to B. So this is the volume, the formula to find the volume of the rotation. And also with the same analogy, if now we rotate the y-axis, so the radius now will be the function of x. So the same analogy for the volume, it's the circle area, so pi r squared fy squared times the thickness delta y, or for the small thickness, it will be equals to dy times dy integral. So I can put out the pi. So I have pi integral AB from fy squared dy. Let's see the example. Find the volume of revolution of x squared plus y squared equals r squared over the x-axis. So we rotate the x-axis, and this is the circle equation. So that means we will rotate this and we have the circle and the radius of y. So that means we have to express this equation into y equals to. So we change it, y squared equals to r squared minus x squared. And then using the formula, we can put it in the formula. The volume is pi y squared dx with the region from r until negative r until r. And then we can do this. So we will have we will replace the y. So this is integral negative r until r squared pi, I put it out, r squared minus x squared dx. The variable is x, so r squared become r squared x minus x squared become 1 over 3 x cubed pi, and then I can put the border negative r until r. And you can use the definite integral method to find the volume. So the volume will be equals to 4 pi r cubed over 3. So replace x in here, yeah? Minus pi r squared negative r minus 1 over 3 negative r cubed. You will get that early. Number 2, find the volume of rotation if y equals to x rotated from 0 until h. So if we draw y equals to x is this, from 0 until h. So we will rotate this and I will have this, a cone. So that means we have to use, because x is rotated, so it's integral from 0 until h pi y squared dx. we use the x because we rotate the x-axis. So y equals to fx, so y squared equals to x squared. So we put it into the formula. And then integrate this into pi 1/3 x cubed 0 until h. Put it into the definite integral 1/3 h cubed minus 1/3 0 cubed. So it's 1/3 pi h cubed. Number 3, the curve is rotated over the x-axis through 360 degree. Find the volume between -2 until 2 and the x-axis, between the graph and the x-axis. So we rotate this. The graph of 7 minus x squared will be this. You can see it's a quadratic concave down from -2 until 2. And then when we rotate, it will be like this. You can see on the right. So we can just put it in the formula. So the volume will be pi integral of fx squared dx. So pi integral between -2 until 2. You can use it directly because both of them are in the positive y-axis, yeah. So the y is 7 minus x squared dx. And I can expand this minus 2 until 2, 49 minus 14x squared plus x4 dx equals to pi, this is 49x minus 14/3 x cubed plus 1/5 x5 between -2 until 2. So I can just calculate it. Pi, okay, this is 49 times 2 minus 14/3 times 2 cubed plus 1/5 times 2, 5. I put bracket minus with 49 times -2 and then -14/3 -2 cubed plus 1/5 -2, 5. And the result will be equals to 2012 over 15 pi. That's it. So this is the final answer, the volume. And here's some exercise for you to do the self practice. Thank you.